Hello and welcome. We are working on section 1.5 today, which is determining limits using algebraic properties. So there are properties to limits, and you are looking at some of those rules right now, where it says let b and c be real numbers and n be some positive integer. And also let f and g be functions such that they are defined when we are approaching a value of c. So, yeah, and c was a real number. So as I approach some real number, I do come out with a limit L for f, and I come out with the limit of k when I'm working with the g function. So there is a property called the scalar multiple property, which basically says if I have some number, b, which is a real number, times a function, I can essentially think of this as the limit of the function and then multiply it by that scalar b. So it's almost, I think of it as that b coming out front. I calculate out my limit, and the limit of f of x as I approach c is L, so I end up with b times L. The sum and difference property says if I have two functions that are added or subtracted together, I can think of them individually. I can break them up and say the limit of f of x plus the limit as x approaches c of g of x. So I can calculate each of these individually. The limit of f of x was defined, to be L, and the limit of g was k, so I get L plus k. If this had been subtraction, then I would have the minus sign. So plus minus, plus over minus, those stay together. Product, same thing. The limit of f of x times the limit of g of x. And we were approaching c in both cases on these limits. So I end up taking the result of each limit. This one had a limit of L and g has a limit of k, so I get L times k. Quotient, I think you can see how that's going to play out. And then finally, the last one with the powers. So this is an m over n, an m over n power. So essentially, I'm going to work the inside of my function first, come out with that limit. That limit is L. And then I will take the limit and raise it to that outer power of m over n. So those are the properties, the rules that we have to play the game by. And let's take a look at some examples. So example 1, consider the graphs of the functions f and g given below. I notice there's some discontinuity points. We got some jumps. We've got just holes. So it's kind of a mess. Find each of the following limits. So I first spot that there is a sum of two functions. So I'm going to break this up into an f of x and the g of x and separate out each of those limits. So that's the property at work for sum and difference of two functions. And now as I approach 1, which is happening right there, x is 1, I notice from the left side I'm coming into 2, and from the right side I'm coming into 2. So I get 2 for that limit. And for g, as I come into, what are we coming into? Into 1. So in this region, as we come into 1, I'm approaching, looks like 1 as a height from the left as well as the right. So this is a 1. Answer is 3. G of x, this one, I'm going to have the limit as x approaches 3 of g of x divided by the limit as x approaches 3 of f of x. And now let's analyze each of these. We are coming into 3. Oh, I should do f first, shouldn't I? As I'm approaching 3, right here, from the left, it looks like we're coming into -2, and from the right side of 3, we come into -2. So I'm going to have -2 for my f of x. Oh, now I see why. G of x, we want to come into 3. Right there's 3. Oh, so both these functions are coming into the same height. That height is 0. The answer is 0. Operations on limits and limits of composite functions. Well, the composite functions make it fun. The standard rule for finding the limit of a composite function looks something like this. So we identify first off that we do indeed have a composite function. We have that nested function going on. Now, read what the rule says. Take the limit of the function that's inside. So I take the limit of g of x as x approaches a, and then I apply just the function evaluated at some number once I have that limit evaluation going on, okay? And it's a nice rule, but it's not always so easy to follow. And it says, while it's useful, this rule can be very easily misinterpreted by assuming its converse is true as well. This is certainly not the case, because if f of x is not continuous at x equals k, or if the limit of g of x does not exist originally at x equal a, then we cannot apply that property above. So we simply can't determine anything conclusively about these limits. We have to run a little deeper into these issues with our standard limit properties, which means often we'll want to come into a, I'm looking for it, from the left and the right side. So it says, recall from above that the limit of one of them's L and the other's K, then we can add the two together if it's a nice simple function. The problem with the rule above is that it doesn't address the cases where either or both of these limits fail to exist. Here we had, a nice definition of each limit for f of x and g of x. But what if one of these turned out to be D and E? Then is the sum of them D and E? Maybe, maybe not. We actually have to dig a little deeper. We have to look from the left and the right side and go back to the very basic interpretation of limit or definition of limit. So example 2 says, let me flip my page. Consider the graphs of f and g given below. Find each of the following limits, and I notice this is my g of x, and then I have the first graph is my f of x. And it says, what's the limit as x approaches 1 of f of g of x? So I'm going to try and do the inner function evaluation for that limit, and then take that result and plug it into f. So as I look on the picture of g of x as we approach 1, as I approach 1, it appears that 0 is the result. Now I take 0 for this answer and plug it into the outer function f. So f of 0 is 2. That wasn't too bad, was it? That was nice. It behaved so nicely. How about the limit as we approach 2? So I'm going to try and find each of these limits, the limit as x approaches 2 of f of x, get that answer, and then let's multiply it by the limit as x approaches 2 of g of x. F of x at 2. Ooh. As I approach 2, I have a little issue going on. What about the other one? As I approach 2 on this one, not so much of an issue, right? I get this location 2, 1, and so they're both coming into 2 from a height of 1. But because this one, I really have a D and E, it forces me to evaluate this a little bit deeper. So I'm going to evaluate the limit as we approach 2 from the right of f of x times g of x. And I'm going to look at the left side of 2 of f of x times g of x. All right, so from the right side of 2, it appears that we have a height of 1, don't we? I'm coming in from the right of 2. That's going to give me a 1. From the right of 2 for g of x, I'm also coming into a height of 1. So I get the limit from approaching 2 from the right as 1. Now what about the left side? The left side, I'm coming into 2 from the left, I get a height of 0. And 2 from the left side on the g of x, I still am at a height of 1. So I get 0. And now, without a doubt, I can say the result, I can do the therefore, 3 little dots in math is therefore. Therefore, this does not exist because the left did not equal the right. So these two are not equal, and for that reason, we do not have a limit. All right, let's look at C. C says the limit of f of x. All right, I want to clear the screen so I can really focus in on this one. The limit of f of x. Well, kind of the rule was I can take f evaluated at the limit as x approaches 0 of this inner function f of x. All right, so over to our picture. As I come into 0, from the left and the right, it agrees at a height of 2, doesn't it? So I get 2 coming out of here. And now what is f of 2? Ooh, f of 2 doesn't exist. So let's just say, let's write this in here. F is not continuous at x equals 2. So it's not a dead end, which is what you would kind of think it is, right? But it's not. So I'm going to go back and analyze this limit as x approaches 0 of f of x. How did it come into 2? Well, it came into 2 from underneath, right? So it's coming into 2 from under, a little less than 2. So now when I go and evaluate f of 2 from the underside, then I get an answer of 0. Do you see how I did that? I evaluated, I knew that it wasn't continuous at 2, so that means I need to analyze just a little bit deeper. The way that I get to the height of 2 is coming from below 2. So now when I evaluate the function, this outer function f, I'm bringing it from the underside of 2, which means to me, I interpret that as 2 from the left, something a little smaller than 2. So that's how I ended up with 0. See, I told you these get funky. They really make you think. Okay, so we've got A and B here. Example 3, consider the graphs of the function f and g. Find the following limits. All right, f plus g. Let's see if this can be an easy one. The limit as we approach -1. Oh, -1, we've got a discontinuous spot there, don't we? So, right away, I think there's some issues going on. So the first thing I note is f is discontinuous at x equals -1. And what about g? How's g looking at -1? It also is. G is discontinuous. Oh, we're just hitting roadblocks left and right here at -1. So I'm going to go ahead now and evaluate this from the left as well as from the right. because that's just what we have to do. So plus g of x. We're going to evaluate one of them from the left, and we will also evaluate from the right. We go back to that very basic definition of a limit. Sorry about that. Of a limit using the left and the right approach. Okay, so left of the left side of f would get us a height of -1. Because if I'm coming into -1, x equals -1 from the left, I get -1. G of x from the left side looks like it is a -2, giving us -3. All right, let's look from the right side. From the right side, I'm coming into -1 from this side, and I follow my graph, and that brings me to a -2. And G coming in from the right side, looks like we end up with a height of -1. Woo, looky there. These agree. These agree on left and right side. So we have a limit. Woohoo! Therefore, the limit is 3. -3. It always pays to go looking at those left and right sides. All right, let's look at 1. Or B, which is x approaching 1. F and g of x plus 1. Ugh. So, alrighty. At 1, the limit does exist. It's not continuous, but the limit exists at 1 for f of x. And then we are sliding this over, aren't we? We've got a slide going on. So as we approach 1 plus 1 is 2. Looks like discontinuity going on there. So I want to, G is discontinuous at x equals 2. That's going to force us to evaluate left and right sides once again. So I want to evaluate from the left side of f of x plus g of x plus 1. And then we also need to evaluate from the right side. All right, this f of x is pretty easy. From the left side, we're approaching a height of 2. G from the underside of 1 would be less than 1 plus 1 will give me something a little bit less than 2. So I'd be coming in from this way, and that appears that we have a 2. Okay. Approach from left of 1, right? Now, the right of 1, something a little bit bigger from 1, we still approach 2, a height of 2 for f of x. Now, if I put something in a little bit bigger than 1, it gives me something a little bit bigger than 2. So I'm really kind of looking at g from 2 plus. 2 plus side means I'm coming into 3, which gives me a 5. These are not in agreement, left and right sides, so therefore the limit as x approaches 1 of f of x plus g of x plus 1. It takes a lot of writing on limits. Don't shortcut it because it will get counted wrong. This is DNE. Left didn't equal right. All right, we have a few more to go, don't we? This is example 4. I'm going to pause this video and record it and then come back and do example 4.